Hi everyone, sorry I'm not in today, but I'm not feeling that well, but I thought I felt well enough to make you a quick video to go through quarks and leptons, lesson 2.1. I think the lesson's actually called Particle Zoo. So, um, I don't know if you know, but when we when we come up with particles in physics, we don't just sort of make them up, we need to try and find them. So at the Large Hadron Collider in CERN, they have a particle accelerator, so it makes particles go fast, and they crash them into each other, and they see how they behave in a magnetic and electric field, and then they can tell things about their charge, their mass, their energy, and things like that. So this picture here is one of the original pictures from CERN. I actually have a picture of this at school. I'll show it to you next time I'm in. And it is the creation of a particle called a pion. Okay, and you can see the track. The collision would have been here of two particles, and then this track here is showing a pion. Okay, and the scientists would have analysed the radius of the circle, and they would have been able to tell lots of things about its charge and mass. So we're going to be able to explain how we scientists can find new particles, be able to state whether new particles can be predicted, and be able to describe some strange particles. Now, first thing to talk about is cosmic rays. Now, cosmic rays are high energy particles from stars. They interact with atoms in the Earth's atmosphere and they create showers of particles and antiparticles, because as we know in pair production, energy can turn into, or photons of energy can turn into particles. Okay, so they interact with atoms in the Earth's atmosphere and they create showers of particles and antiparticles, and we can detect those at ground level. We can also detect particles through something called cloud chambers. They're chambers filled with like ionized gas, and we can create some short-lived particles and antiparticles there. For example, muons, which are like heavy electrons, pions and kaons. And then we mesons, which are pion and kaons, which we can now detect in cloud chambers. They were actually predicted before they were found, but once you predict a particle, you need to go away and find it. So, can you think, maybe pause the video, what particles have we talked about so far, and how would you go about sorting them? Okay, so you've probably got a list of things here that we've talked about. So we've talked about electrons, protons, neutrons. We talked about their antiparticles, so positrons. So what about things like, we talked about the bosons, so the K boson, gluons. Okay, how would we sort them? What would we sort them by? Okay, so you might have come up with some ideas like, we might sort them by mass, we might sort them by charge, we might sort them by type, we might sort them by where they're found, we might sort them by what job they do. I'm going to go through a list of particles now. You'll need the table, so when I put the table up, pause me, draw the table, and then we can fill it in. You'll need a bit of space for each one. So this is the table. You need the particle and its symbol, its charge, what its antiparticle is and its antiparticle symbol, what that charge is. This is relative to a proton. What its rest energy is and how it interacts. Okay, so just press pause, draw this out, and then you can press play again. Okay, so the first particle is a proton. We've obviously talked about protons before. It has a relative charge of +1. And then you have the antiparticle, which is an antiproton, which has a relative charge of -1. Okay, and then you have, it has a rest energy of 938 mega electron volts. You don't really need to remember the rest energies because they're given to you on the data sheet. And it interacts, protons can interact through the strong force, the weak force, and the electromagnetic force. pause me after each one of these and then you can fill them in. Okay, next we've got a neutron, which has a symbol N. It has a relative charge of 0, and an antineutron, which is exactly the same, which also has a relative charge of 0. Its rest energy is slightly higher than a proton, 939 megaelectron volts. It's because it's slightly heavier, very slightly. And it interacts through the strong and weak force. It does not interact through electromagnetic force because it has no charge. Oh. I don't know why those are missing. 1 second. Okay, I've gone to my PowerPoint and it's better now. So then we have a neutrino, which has a symbol. It's like an italic V. Okay, it has a relative charge of 0. Its opposite is an antineutrino, which will obviously also have a relative charge of 0. And it also has no mass, so it has no energy. It's a very strange particle. Okay, so its rest energy is 0 and its interaction is through the weak force. Okay, and then next we have a particle called a muon. Its symbol is a muse, which is like the same as mu that you use for micro. So it's like an M or a U with a long tail at the start. Its particle is actually negative, so it has a charge of -1. Its anti-muon is positive, so it has a charge of +1. It's quite light, okay, so it has a charge of 106 megaelectron volts, and it interacts through the weak and electromagnetic forces. It is not involved in the nucleus, so it does not have the strong force. I think I missed out electron. The electron one's there as well. Electron is -1, positron is +1, and then you have your 0.511 rest energy. It interacts through the weak and electromagnetic, not strong because it's not in the nucleus. Then you have the pions. So you get 3 types of pion: pion minus, pion 0, pion plus. They have a symbol pi. Okay, and they have relative charges each of -1, 0, -1. Their antiparticles are of each other. So a pion minus, its antiparticle is a pion plus and would have a charge of +1. Okay, pion 0 is 0, and then the pion plus antiparticle is a pion minus. So they're sort of the opposites to each other. Okay, the rest energies are there, really similar rest energies, and they interact through the strong and electromagnetic force. In fact, I think they're responsible for the strong force. They're the interaction particle for that. And then last but not least, you have the kaons. So kaons are complicated. We talk about them a bit later. You have their symbol is a big K. It's a capital K. Kaon minus, kaon 0, and kaon plus. Their charges are -1, 0, and +1. Now they do have antiparticles, but it is complicated, so they have more than one combination of antiparticles, so we'll just leave that for now. But the K minus antiparticle would have a charge of +1, and the K plus particle would have a charge of -1 there, so they're opposite to each other. Their masses are all really similar, the center one, the K0, being slightly different, and they interact through the strong and electromagnetic forces. Where it says charged here, it means the charged ones do. The zeros would not interact through the electromagnetic force. Okay. So the way that we group particles together is by the types of forces they interact through. So the group of particles that interact through the strong force are called hadrons. They tend to interact through the weak electromagnetic force and gravitational forces also. So if we go back to our table, anything that interacts through the strong force is a hadron. So protons, neutrons, strong pions and kaons, and there's a couple of other ones. There's a sigma as well. Now the proton itself is actually the only stable hadron. All of the others would decay through the weak interaction. So basically all of the others would decay into a proton eventually. They would turn into a proton. I know in a nucleus, a neutron wouldn't turn into a proton on its own, okay? But if we isolated them and left them on their own, they would all turn into a proton. It's the only stable hadron, okay? And you often get asked that question in an exam. Then we have the leptons. So the leptons are particles that interact through they don't interact through the strong force, basically. So they can do weak, electromagnetic, and gravitational. So if you look in our table, okay, it's these three: the electron, the neutrino, and the muon. They are all called leptons, and leptons themselves are fundamental, which means they cannot be broken up into smaller parts. They are the smallest particle you can get, whereas the hadrons can actually be broken up into smaller parts called quarks. Okay, now if we just talk about energy then, so when you go to the Large Hadron Collider, you smash together particles. Well, you don't, but the scientists do. This is actually a picture of me and one of my ex-students at the Large Hadron Collider. It was just being built, actually. It hadn't actually started doing its experiment. So yeah, and what we can say is that the total energies of the particles before the collisions, so they're traveling through this tube and they meet here and collide. So their energy before the collision will be equal to their rest energy. So if they were stationary, how much energy would they have? And then their kinetic energy as well, because they'd have kinetic energy too, because they're moving. So that any new particles you make and antiparticles after the collision, so any particles you make here after the collision, that will be equal to their rest energy plus their kinetic energy also. So the particles are coming together, they have kinetic energy and a rest energy. The reason they have rest energy is they have mass, and mass can be converted into energy using Einstein's equation E equals mc squared. We did that in GCSE. So they have an energy because they are a mass and that can be converted into energy. And then they're also moving, so they have kinetic energy too. So whatever energy you've got before the collision, you must have at the end. So if you pick up all the pieces after the collision and add up all their energies together, you should have the energy you had at the start. Okay, so that idea uses the conservation of energy. Okay, so the rest energy of the products equals the total energy you had before minus the kinetic energy of the products. Okay, so this will tell you how much mass they have. So you how much energy did you have before? Take away the kinetic energy of the product, so how quickly they're moving basically, and you get left over with their rest energy, and you can calculate their mass using E equals mc squared to find their mass. So there's a question here for you to have a go at. If a proton and an antiproton, each with kinetic energy of 2 gigaelectron volts and a rest energy of 1 gigaelectron collide, what is their total energy in joules? So you need to sort out what it is in gigaelectron volts and then convert gigaelectron volts into joules. So I'm going to leave you to do that, and hopefully when someone comes up with the answer, you will be able to show how to do it to everybody else. Okay. Oh, I had an animation. Look, that's cute. There you go. That's when they collide and they make these particles. So this is a really nice summary of where we are and where we're going. Okay, so we talked about matter and antimatter, and then we've talked about the two groups. So we've got leptons, which are electrons, muons, and neutrinos. They are fundamental, so they can't be broken down anymore. We then go to hadrons, which was anything that interacts through the strong force, and they can actually be broken into two different things. So you've got the baryons and the mesons, and we're going to start to look at these in more detail next lesson. But basically the baryons are protons and neutrons, and then I think the mesons are everything else. Okay, so this is a nice flow chart, and what you could do is fill in these little boxes telling me what belongs in each thing. So you've got matter and antimatter. What is it? What are the leptons? What are the hadrons? And then we'll start to look at the baryons and mesons. Okay, there is some questions in the book, but I haven't got my book at home to show you. But if you wanted to have a look at the questions in the book, the book is on my shelf, and you are more than welcome to grab it and take a photo of the questions and the answers in the back. Okay, take care. Bye.